Okay, I will pick 25 then. If you don't want to pick, I have xy plus y squared minus 2x equals 0, and they're giving us the point 1 comma negative 2. Okay. So again, the same situation. I cannot solve for y. This is not a linear equation in y, it's quadratic, and it will be difficult to solve that and then differentiate. So we will apply implicit differentiation, meaning we're going to differentiate the left-hand side and differentiate the right-hand side. I will put some landmarks in there, reminding us, since we are asked to find dy over dx, it tells us that y is a function of x. So this has to be treated not as a variable, but as a function of x. This has to be treated as a function of x. So then the first step is I have to apply which rule for this? Which rule is applicable here?
Product.
Yes, excellent. So the first function prime. Good, times y, very good, plus x times the second function prime. What would you write? What should we write for the second function prime?
XY.
dy over dx plus. Can anyone differentiate this function squared? How do we differentiate a function squared?
Y.
Yes, times
dy over dx.
Thank you very much, times the inner function prime. Awesome. Now we are here. How do we differentiate negative 2x? Minus 2. Okay, silly question. What is 0 prime?
Zero.
Yes. Good. Now from this point on, only algebra. This is algebra. This is the variable that we are after. Y has to go to the other side. 2 has to go to the other side. And here we factor out. So we have x plus 2y times dy over dx equals 2. It was negative. It changes its sign. It was positive. It changes its sign. Can anyone give us the last form for dy over dx? Again, this is algebra. Calculus was up till here. Beyond that, just algebra.
2 minus y over
Oh,
x plus 2.
thank you very much. 2 minus y over x plus 2y. Now, we are told to evaluate, find this when x is 1 and y is negative 2. Here's how we write it. Two minus negative 2, 4, over 1 minus 2 times 2, which is 4. So this is 4 divided by negative 3, or negative 4/3. So in this problem, not only that we determine dy over dx, yes, still function of y that we don't have, I agree, but we were able to find the slope of the tangent line to the graph of y at this point. How much is it? Negative 4/3. And that's how we apply implicit differentiation. Will anyone like to look at another example, or we move on?
number 19.
With pleasure. So let's look at number 19. I'm on page 4. Number 19. So let's take a look. Where are you, 19? I see it. So in 19, we have x squared plus y squared equals 1, and the given point is 1/2 the square root of 3 over 2. Awesome. Very good pick. So we are asked in step number 1 to find dy over dx. In step number 2, we're asked find dy over dx when x is 1/2 and when y is the square root of 3 over 2. These are the two questions. In order to find dy over dx, I will not solve for y, because then I make my life more complicated. It turns out that this equation can be solved for y, but it will be more difficult to find the derivative afterwards. It's easier if I use implicit differentiation. I'm going to emphasize which one is a function by putting a dot underneath it so we don't make an error. Good. So then can anyone differentiate x squared?
2x.
Very good. Plus, can anyone differentiate a function squared?
times dy over dx.
Excellent, brilliant. And can anyone differentiate 1?
Just 1.
0.
Thank you very much. Every constant prime is 0. Perfect. We are after this. I don't even need to factor or do anything else. I will move 2x and divide by 2y. So dy over dx equals negative, because I move it, it's negative, 2x over 2y. Of course, I'll simplify these two. And I finally get dy over dx is negative x over y. When they're asking us to find when x is 1/2 and when y is the square root of 3 over 2. I just have to plug them in. Negative is outside. The numerator is 1/2. The denominator is the square root of 3 over 2. I have to flip the denominator. I'm going to go to the next page. Okay, page 5. Good. So this is negative 1/2 times 2 over the square root of 3. These will go away. And I get negative 1 over the square root of 3. And if you want to rationalize, as you probably at some point in time in math have done that, you get negative the square root of 3 over 3. So what have we accomplished here? We determine an expression for the derivative of y with respect to x. Here's the expression, negative x over y. And we were also able to determine the slope of the tangent line to the graph of y when x is 1/2 and y equals the square root of 3 over 2. And what was it? Just plug it in. Just algebra. Plug it in and get the answer. Any questions? Any questions? Do you feel a little bit better about implicit differentiation now? Is there a yes? Is there a no? Do we need more examples? I don't know what to.
I have a question.
Yes?
Last page.
Yes.
Why do you exclude the dy over dx just from the y part?
Cece, can you repeat the question, please?
So you see how we have the 2x plus 2y times dy over dx. Why did we just add dy over dx to the 2y?
Because x squared doesn't have y in it. When I differentiate x squared, I only get 2x. I cannot add something that is not there or multiply by something. This first term is just x squared. The second term is just y squared, but this is the function. This is not a function. This is just the independent variable.
Okay, thank you.
Better?
Yeah, it's better. Thank you.
Thank you. Good. Other questions for me? So let's continue with another application. Okay, related rates. Still another application of differentiation. So how many applications we know so far? 1, graphing. 2, absolute, max min. 3, word problems in which we find max min, like the one we just did with a cylinder. And number 4, implicit differentiation that we just did. And number 5, related rates. Number 6, the last one, sorry about that. Related rates. And the last one, approximations. That's it. And this is where chapter 3 ends. But we still have these two to work on. Okay, so let's talk about related rates. Imagine that we have a balloon. It's completely deflated. And then we pump air in it. And let's suppose it's supposed to be a sphere. So let's say it looks like this. We continue pumping air, and then it looks like this. We continue pumping air, and then it looks like this. No air, little air, more air, more air. So notice what happens here. The volume changes, volume of air. It had very little, more, more, more. So the volume is a function of time. Why a function of time? Because at this point, at time 0, very little air. And a minute later, it looks like this. So the volume increased. Another minute later, it depends on time because I need time to blow air in the balloon. It looks like this. And then it looks like this. So the volume is a function of time. Also, look at the radius. And look at the radius. Radius is also a function of time. What else? Look at the surface area. Smaller, bigger surface area, bigger surface area. So S, surface area, also function of time. So all these have derivatives. Why? Any function has a derivative, right? So with some exceptions, of course. But the volume changes. So there is a derivative, right? The radius changes. There is a derivative. The surface area, there is a derivative. So because the volume of a sphere, and I'll give you the formula, so this is my page coming up 6. So the volume of a sphere is 4/3 pi r cubed. So this is the relationship between two functions of time. This is a function, this is a function. They're both functions of time. So they are related. These two functions are related by this equation or this relationship. Their derivatives, will be also related by an equation. Because there is a relationship between two functions, their derivatives will also be related by a different function, by a different equation. Let's try it. So this is a function of time. This is a function of time. When I differentiate this, I get dv over dt. I have 4/3 pi. When I differentiate this, it's a function. 3 r squared times dr over dt. I will simplify. So then the derivative of the volume is related to the derivative of the radius. Why? Because the two functions were initially related. Their rates are also related or connected. How? Through this equation. So their functions were related, or they found themselves in the same equation. Their derivatives are related by a different equation. So that's the meaning of related rates, related derivatives. They are in the same equation. They are influencing one another. That's what it means. So let's take a look at a few examples. This is page 364. Please choose. Find the indicated rate. Anything you want from 1 through 20. I would like to start with a simple one like 11, and then you choose the next one. In 11, we have y equals natural log x. Find dy over dt, which means y is a function of what? If I'm asked to find dy over dt, that tells me that y is a function of which variable?
D.
Of course, absolutely. When x is -9, and when dx over dt is 0.25. So let's analyze first of all what we are given. I'm asked to find dy over dt, meaning y is a function of time, or t. T doesn't have to be necessarily time. I'm also given the fact that dx over dt is 0.25. So x is also a function of time. That's the reason why I put those dots underneath. So we remember that both are functions of t, or time if you want. So I cannot plug in anything till I find dy over dt. After I find dy over dt, then I kind of plug this in. It's very similar with what we just did a few minutes ago with implicit differentiation. Very similar. It's just that it's one step further. Why? Because now x is a function of time as well. Initially here, Sissy had a question. She said, what are you doing with this? And she was right. Well, x is not a function of time. That's why we have to treat it as an independent variable. So when we differentiate x squared, we get to x, and it's done. But now, it's one step further, because we have two functions whose derivative are in a relationship as well. They are themselves in a relationship, but also their derivatives are in a relationship. And this is what we want to determine. So let's differentiate implicitly, and let's see what happens. Who would like to differentiate, keeping in mind that there are both functions?